All right. Hi, everyone. Yeah. Hi. So this is like a very introductory session to what is supercomputing and what are student cluster competitions. So like the talk is structured in that way. So initial 10-15 minutes is about like a way to look at supercomputing, like sort of define it in some way, as well as to see how it influences your daily life, our daily lives. And after that, a major chunk would be UA talking about the experiences and some behind the scenes of these student cluster competitions, what they are, what's involved there, and what sort of things you can take away from those competitions. So yeah, let's start. Yeah, so just reiterating before we start, in the meantime, there's this check-in form. So MLH, Major League Hacking, is our sponsor for this event. So if you could check in here, that'll help fund the pizzas after the event. So yeah, so what is supercomputing? Where do you find it? And why are we talking about it here? Just a note before we start. So supercomputing and HPC are two terms that are sort of interchangeably used, and HPC stands for high performance computing, and we are going to use it interchangeably during the course of this session. So yeah, where? If we sort of think about it, supercomputing is actually everywhere, and it's influencing this from the smallest things that we use on a daily basis. So here are some examples. Something like Face ID or Touch ID, or something that we use to unlock our phones. We use it multiple times a day. Something like this was actually built on supercomputing clusters. Like these clusters were used to bring forth such a technology. Weather forecasting, live weather forecasting. So whether it's just updates of how the weather is going to be today, the next day, or something a bit more detailed where you're trying to look at how the winds are flowing all over the earth on a, So that's the thing to your right. It's a website, you can check it out, earth.nullschool.net, and it's like a live feed of the winds, the different wind pressures and speeds. So if there's a storm, you can actually see how things are happening. And that's all data gathered from US weather bodies and from other communities all over the world. COVID vaccine development. So something like this was sped up a lot because of a huge amount of compute which was used to speed up the process of developing a vaccine and bringing it forth for everyone in, I guess, less than a year. Car simulations. So whether you're old school stuff of designing a car or designing F1 cars, or some new gen stuff of self-driving cars, training these self-driving cars to go about autonomously, whether they're using any form of LiDAR or just normal cameras, motion planning and all. All of this requires a lot of compute, and that's all. The foundation is supercomputing. And some AI stuff that's happening nowadays. So whether it's the Gmail auto-compose thing, or something like Grammarly that you use to analyze your text on a real-time basis, or if you would have heard of like GPT-3, which is, I guess, 2 years old. So generating question answer sort of examples of, you feed the AI some text and ask some questions and you get answers to it. Or the latest one's Stable Diffusion, where you can the computer can generate images which are sort of like just given a description, a sentence as a description. So all of this modern AI stuff, you can't do it on a single GPU or on your laptop. You need large data centers and supercomputers to actually train these large models. And in the case of GPT-3, even the end product, when you are using the final trained model, which is called the inference, even that inference can't fit on a single GPU because the model is so huge. and maybe something else like Disney movies. So this animation and the graph below, it shows that the huge amount of computers that are spent in designing these movies from scratch. And some examples like Frozen or Tangled or Big Hero 6, these all were sort of designed on these large workstations and supercomputers. So that's more about the where. So I guess let's talk about what is supercomputing. Yeah, it's supercomputing. So if there's one word that you take away from the definition, it's performance. So supercomputing is all about extracting maximum performance from whatever hardware is at your disposal. And next, designing your hardware and software in such a way that you can, go beyond. So some things to think about, like how these supercomputers differ from the laptops that you have in front of you, is like you typically do not have any graphical user interface. There's no eye-catching Apple Mac OS X interface or Windows on these machines. We typically deal with command lines, and even the operating system is sort of tuned to be the bare minimum to just handle scientific compute workloads and handle I/O, memory, so on and so forth. You do not have other higher level stuff which may be more common on our laptops. And the hardware and also the software are sort of specially tuned, and nowadays it's co-designed. So both are the design. Earlier this design used to be sort of in silos, but now to sort of target higher performance, these hardware and software are sort of co-designed in order to achieve maximum performance. And this is how these supercomputing clusters or data centers look like. Just cabinets of servers all working together to solve a problem. And that's one term which will probably, if you search about supercomputing, you'll hear a term called exascale. And that's sort of relevant now because it's an achievement that the supercomputing community has achieved this year, which is exascale. And what's that? So instead of giving you a technical definition, just maybe a different analogy, that if all of us, the entire population of Earth, tries to do some calculation for more than 4 years, this new exascale supercomputer can do it, which is called Frontier, can do it in 1 second. So that's the power of this largest supercomputer, and that's the scale of that's what exascale has achieved. So with some I hope you have some idea now as to how we define or what is supercomputing. So why are we talking about it here? Why are we conducting this workshop? And why are we trying to sort of recruit you for these student cluster competitions? So we'll try to answer all of that here. So why do we need supercomputers? So this is another recent news, something that the city of Orlando achieved. So this is something, another buzzword called digital twin, where you're trying to create a virtual replica of something from the real world. So here they have created a digital twin of certain counties from Orlando, and how that, so it's a 2-scale exact mapping of a real world area. So how that helps is, if you're doing some city planning, if you're trying to make new roads or construct new buildings, so on and so forth, you can do it on a virtual twin, and try to achieve better safety, more reliability, so on and so forth. Another thing from, I guess, 2 years or 3 years back was this picture of a supermassive black hole. So how this was constructed was when the researchers did use the Frontera supercomputer at UT Austin, and it's only possible because there was so much scientific data to churn through and go through, and it's only possible with supercomputers. Or if you want to do something in the future, if you want Elon Musk's vision of Cybertruck on Mars to become a reality. That's not going to happen without supercomputers. So yeah, talking a bit about AI and natural language processing, these again things you might be hearing in the tech world. So GPT-3 came out in June 2020, and in the past 2 years, these are all large models which have come up. So if you compare the sizes, GPT-3 had 175 billion parameters, and now that has been growing. And the largest one, at least which is publicly announced, is from Google, which is 540 billion parameters. So like, yeah, before this, everything was pretty small. The language models, the AI models were pretty small. And in just 2 years, you have such large models, not just from different companies, but the ones marked in red are open source as well. So all of this training can happen only on supercomputers. You need hundreds of GPUs to train such large models. And yeah, another just a small thing. So if you notice the largest bar in this graph, so this is from some conference, from some recent conference, and it shows like the number of GPUs, NVIDIA GPUs, which belong to a particular institution. Now, typically we think that supercomputing belongs to like research labs or national laboratories which focus on core research, and but if you see, the largest number of GPUs are with Meta. So it's not just it's no longer limited. The old idea of supercomputing being limited to research scientists and national laboratories is no longer true. You have industry which is targeting and actually having the largest number, the largest compute. So yeah, just imagine 16,000. So A100 was their last, most powerful GPU. Like the newest one is H100, I guess. But A100 was super powerful. It's a single GPU contains 80 GB of memory, and they have 16,000 such GPUs in their private cloud and 5,000 something GPUs in their public cloud. So imagine what they're trying, what sort of experiments, what sort of products they're running on such a high amount of compute. So yeah, why are we trying to do this this workshop and this thing? So we observed that the computer science department does not have a core HPC course. There is one course called AM250, which is an intro to HPC by the Applied Maths department. And if any of you are interested, yeah, that's a great course for an intro. But again, it focuses on the programming aspect, which is awesome. But if you want to understand, if you want to learn about designing such supercomputers, yeah, that's a bit missing from the CSE curriculum. But you do have background courses that help you sort of understand what it takes to build a supercomputer. But there's no hands-on experience, there's no hands-on assignment which helps you actually understand what it means to work on a supercomputer. But as we saw earlier, the industry is going towards this thing, and another term which we talked about was exascale. So just a slide about what is this exascale. So there's something called top 500, which is it's a body, and it's essentially a list of the most powerful supercomputers in the world, and it is being maintained since 1993, and this list is updated twice a year, once in November, once in June, which coincide with two supercomputing conferences. One is SC, which is going to happen in 2 weeks in Dallas, and another one is ISC, which happens in Germany in June. So yeah, in 2022 is when we achieved this exascale, and what exascale is like, the processor can do 10 power 18 calculations, floating point operations per second. So that's what exascale is. And if we look at this graph, and it's a projection graph, so 2022 is where the lower triangle was achieved, which is more than 1 exaflop. And if we sort of do a regression, in 3 years, this performance would double. So that's the projection, and which implies that supercomputing is on the rise. So it's good if we understand what is supercomputing and how we can sort of contribute to this movement. And yeah, it's not just research. So these are a few industry supercomputers. So that's Meta, NVIDIA, and Tesla. So NVIDIA EOS is something which is going to come up soon. They had something called Selene, which was ranked 8 on the top 500 list last in June 2022. And it had 8 million cores. The entire system had 8.7 million cores actually. So just imagine thousands of GPUs working together to solve a problem. So yeah, it's, as I said, so these are just examples of how it's not just research labs, but industry who are jumping into this. And a similar topic, which is supercomputing or AI chips. So Amazon has its own custom chip. Google has something called TPU. Tesla has Dojo. Baidu has Kunlun. And apart from this, you have the regular hardware vendors like NVIDIA, AMD, Intel, or ARM. You have these core software FANG-like companies, which we typically relate to as software vendors, but they are jumping into the hardware space, and there is a reason for that, because everybody wants performance because there's just so much to do when you have that huge amount of performance. And on the other side of the spectrum, this is the startup arena. So most of the startups that you see here, whether it's Horizon Robotics, Samba Nova, GraphCore, Grok, these are all startups which have their own custom hardware. So, and you have billions of dollars in play here as well. So, it's not just large companies who are targeting custom hardware, but the startups as well. So, and yeah, this is some snapshots from different job boards. So, I guess this was OpenAI, that's Google. The middle one is Meta, that's Amazon. I guess this is Tesla. So you have jobs which are targeting supercomputing or server platforms and so on. So any skills that you pick up here, if you are interested, you have actual core competency jobs which have started coming up in the past 2 years. And yeah, that's sort of the intro part. And with this, we can switch to UA, where they'll talk about what student cluster competitions are. So in the meanwhile, if you haven't checked in, please do this. This is what funds the pizza. I know it's a bit curvy process, but sorry. And there's another check-in form, not a check-in form, but an interest form. So if you are interested in joining the group, you can do this later. There's no urgency. This is an internal UCSC Google Doc, and in which we just want to know more about your skills and your interests. And we are trying, as we said, we are trying to recruit students for the student cluster competition. So if after UA's talk you feel that you're interested in joining the group, please check this form out. So with this, we'll switch to UA. Thank you.
I'm Yiwei. I'm the first year PhD student here, and I just graduated from Shanghai Tech, which is a school that also hosts a team of HPC team that led the students to go to the supercluster competition. So I have a experience of 2 years that frequently experienced how HPC are working or SCC are working. So I'm going here to give some basic idea of how this supercluster competition are. So why HPC? As the Neo says, there's a lot of needs, and we have to tailor to their demand. And my view of this is that if you want to predicting something like weather, if you want to predict something ahead of time, you have to increase your computing power to let it be predicted before the actual thing or happen. So that's why we are doing HPC because we can make it from 0 to 1 to get the simulation result ahead of time, that we can no matter predict the weather, predict your missile, atomic bomb, or other things that are simulated, or your, for example, the financial market are going to predict it in a few ticks. These are the thematic of the momentum of how HPC works, and how HPC basically, the people who has a CS department learning has a basic view of how C++ or basic compilers are working. And HPC, parallel computing, they introduce some of the programming paradigm that like OpenMP, Fortran, and OpenMPI, and OpenACC, these kind of disaggregation or multi-platform, multi-node disaggregated computing are those paradigm or primitive for you to for the code to compile. So basically, the HPC competition, your input is a bunch of code. For example, MPI code, and your output is as fast as possible running on HPC platform. And normally, we have exactly the same platform we run on. So there's so many hacks that we can do during the competition. For example, we are take about later in the slides, core affinity or topology things, and load balancing for different MPI loads or something. Yeah, and also there's a great idea in HPC is about DevOps, because in production environment, you won't let your server down, or you won't let your service down. So you have to make sure that your service are run in a correct way. And if it's down, you can automatically let it up. Or if it requires some human resources, you can put your message on the Slack to hit something on call. For yeah, because I know so many people in the AWS are on call who is super squeezed by the company. And also we have to learn some basic programming models of how GPU works and how CPU works. And finally, we have to know about the distributed operating system. And in the last, the goal of this talk is basically give you a basic idea of HPC and how which courses you have to take in terms of being a great HPC guy, and let you in our team, because we have literally 4 people who are vacant for the position. And for HPC, basically, we have the timeline. So normally, we have a competition. It's called WEI competition that happens in HK, and normally happens in February to from February to May. There's sort of like 3 months thing. Every week they will assign you a supercluster application that we'll cover later. So and you have to submit result every week. And for June, we have to prepare for the ISC, which take place in Frankfurt every year in Germany. So we have to prepare it beforehand, like 2 weeks from now. Like in November, we have to prepare for next year's ISC. And for SC, we literally submit our proposal at May or something. So you know, if you want to attend the HPC, it's actually a 1 year round. Like you have to take care of every month. So let's give you a basic idea of how those supercluster competitions are working. As now put that the ISC and SC are the 2 conferences that happens in both industry and academia. The ISC is mostly industry work, and the naming is called HPC AI Advisory Council Supercluster Competition. And this advisory council is not the holder of the ISC, so it's a tender of the ISC. So it's super fun. But for SC, it's correlated with the academia conference, which is the top conference in the supercluster fields. And for the entering and or submission, both of them are submitting for a proposal, like to manifest your strengths of the team. And normally ISC take place in Frankfurt, but last year it takes place in Hamburg, so it may change. And SE it takes place in these 3 cities: Salt Lake City, Denver, and Dallas. In ISC, if you go there, there will be a lot of industry conference. For example, NVIDIA, Inspur, and they will give you a demo of how the latest industry are working. SC are merely the academia conference. You can see talks by those PhDs who are giving their latest result on their academia work. And the fun thing is that ISC normally take 4 days, and you can sleep every day. So after 5, you couldn't get access to your HPCs, and you're forcefully to get rest, and you can have a nice dinner and get sleep, and do it tomorrow at 8 a.m. to go back to your HPC desk. But for SC, it's a 48-hour hackathon. It means that you couldn't sleep, so you have to take care of your chassis all around with you, with 5 to 6 people. And the rule is it has a 5 to 6 undergrad, but ISC can take 2 graduate students. And it will be held on field so that no other advisor or other students can gain access to here, to your chassis near your desk. But during the competition, some media or other students will come to you so that how's your application going, running, and how's your score is. And there will be a dynamically refreshed screen to show how the current, the highest score is on the screen. So that it's fairly intense. You know, once other teams are submitting their recent results, you get stressed because you know that your results are not competitive with others. So that'll be great. And it will be a hardware power limit of your whole chassis. Although you can self-design your topology of your high performance computing of different nodes and how they're connected, but you have an overall power consumption of 3,000 watts. And now they will raise it into 4.5K watts because of NVIDIA GPU has already draining so many power. But it's okay, but yeah. So during your power consumption, you have to limit your power. Because, so how to do it? You can hang your program, or you can under throttling or your CPU, and also you can do some other hack like hot plugging your GPU to make you to be compliant to this power consumption limit. And I think for two competition, you can only exceed the limit once, and else you will be kicked out from the final result. And also, you couldn't set up a network during, because if you set up the network yourself, someone else will SSH or it will help you. So you will be fined for, what's that? It's 100K euros fine if you set up a network yourself. And then we have HPC rules exclusive to SC. So to maintain the real-time production possible failure, it has a random power failure that is designed by the organizing committee in the middle of competition. So you have to make sure that all your applications should be snapshotting to the latest and does not hurt the performance. That is super interesting because sometimes some top teams didn't be compliant to that, and they want to make it super fast and to make it be running out before the power shot. But unluckily, like they just lose their all results because some of the result is 48 hours hard limit, but some of the results may take 24 hours. And if they cut in the middle, their 24 hours will never be executed until the end of the competition. So that's super fun. And the second, they officially provide some cloud server resources. So you can use them, these are not. And their cloud servers are normally be used to submit your final result, because some of the simulation results, for example, for weather, could take gigabytes or terabytes. And you use this like Azure things to fast migrate from one server. For example, if it happens in Frankfurt, your server is located in Austin, and you have to migrate your data from Austin all the way to the site. So that's super funny things. And also you can participate to the conference because SC is a conference, right? And for ISC exclusive, it also has something weird like a t-shirt challenge session that's designed for t-shirt, also earn points, because we all know that HPC committee is a very friendly committee that embraces art or something. But it was the end of it was at the end of the competition start. The team's uniform should be, and there's some hide and seek games, like some teams' uniforms are hidden from there, and you have to find it. Get an extra point. And also exhibitors in the ISC conference, because they are all from the industry. Industry can send some random gifts to you, like gives you A100 GPU to send you back home, and yeah, that's super interesting. And for SC20 and SC21 exclusive, because the last 2 years are all go virtual because of Corona, and so in SC20 and 21 we use Azure uniquely, that all the cloud resource they provided with you, they cut the limit of how much of the budget you have. So we know that the Azure machine are cut by, for example, how much time you used, and you get paid for how much for performance of your chassis are. For example, AMD 7742, which is at that time is the latest chassis for AMD. It takes $6 an hour, and they gives our 4.5K US dollars for 48 hours, and you have to use those to as much of the resources that you open, and at least you can deploy your application on your deployed HPC, so that you make sure that your all the budgets are using the right way. So it challenges your dollar per performance. There's kind of that thing that you want to consider. And also it examining the ability of scripts, because the Azure gives us is a bare metal machine. And no, it's not bare metal. It has a shim layer over the bare metal, but it's nearly bare metal. So although it has a hypervisor, but you have to every boot of a newly declared machine, you have to install all the script, install all the basic basic, for example, glibc from all the way to the application. You have to compile it all the way yourself once. So the startup scripts normally is what this kind of competition are testing you. And also you need a 24-hour continuous operation, because it's a 48-hour hackathon. So our plan was to, so if anything goes wrong, send a message on Slack. So anyone who are getting to sleep will not get asleep and go back to the computer and to go DevOps things. And also, if Slarm, which is a scheduler for your work, it dies, you can do it like using your script, automatically reboot it for the live use. And also, aside from the top 500 that mentioned by Nell, we also need to run something called IO 500 for SE, which is testing the basic write, open, read for a large amount of random small files or a large amount of big sequential read for your file system. And Tsinghua University has written one that is beat all other students' file system called MadFS. And other than that, Intel has other file system called Deos and other parallel file system called BGFS or Lustre. So at that competition, you can actually write academia or industry production-ready file system to hack those benchmarks. And for ISE 21 exclusive, they need to require for code challenge part. They need to write a MPI profiler that hook on the all MPI all to all V of WRF, which is a weather application that predict the weather in the future. That's a pretty interesting thing. So you have to get a basic idea of how all to all V are communicated between different chassis, and you have to hook on different MPI calls. Like when it calls, you record all the input arguments, store into a file, and to get a timing of how that MPI LTR are done. So you know that if you're going to interact with the ISC competition, you have to get a basic idea of software engineering or something. At the bottom is an Azure HB60RS VM, which gives you basically two 32-core AMD cores, which is OEM, but 4 of the cores from 0 to 3 in a socket 0 are given to the hypervisor of the Azure's thing. So once the boot up, all the Azure script use these 4 core to monitor how the virtual machine over that layer gives you. And basically, what you can do is to use the remaining 60 cores. And if you get that kind of topology, you can find things, because the socket 1 to socket 0 communication are super slow in terms of MPI all-to-all reduce. So you can give it a percentage, how much benchmark, like 28 core should be assigned on the socket 0, and 32 of them are assigned to the socket 1. That will get a faster result of your final benchmarks. And so how do you rank those HPC applications for supercluster competition? First, as Nell says, there's a 3 benchmark for top 500, which is HPL, HPCG, and HPCC. HPL is a dense matrix multiply, which is A times B equals to C. There are M and K, and M and K are super large. So they use this to basically to tell how many T-flops of your applications, especially GPU, because we normally use a pre-configured binary for GPU on our final machine. So this matrix of the HPL results basically give you how much the performance of your configuration of a HPC does. And HPCG is a sparse matrix multiply. What is the sparse matrix? It means that there's so many zeros in your matrix in terms of the A times B. And A matrix has a lot of zeros, and B matrix has a lot of zeros. So they use a different format to store. If there's a 0, they just leave it and they store the position of if they has a number. So maybe they are using a CSR form. And these are used to test your configuration of communication in terms of different GPU, how they are communicated, and what's the overhead of that. So these 2 metrics are top 500 that used to evaluate how our supercluster or how performant it is. And we are going to doing it in a supercluster competition. And if the highest score every year for ISC and SC will get another credit for it if you are the top one. And then there are public questions that normally we had something we will talk about later. It's all about the applications that come up every year. It literally is from previous year's SC. It will publish some paper, and those paper are requiring the performance, and you will need to reproduce these results from the last year SC's paper. And also maybe there's some industry application you need to run so that you can be more performant than the original paper's result, because you have a better machine and the better talent of the undergraduates than theirs. Every year they also so how to get a score of those public applications, you need the correctness plus the performance, and there has a median or something to calculate those. And for mystery application is that those are not being given like before the competition. You only go into that desk, you can get know that what the mystery application is. And normally we can use some startup script and good package management, for example, the spec, apt or pip or npm to install them. You need to fine-tune your compiler option in the first hand during your run. And for the public application, actually you can know the application beforehand, like 1 month before the competition. So you can pre-compile something and prepare for the competition. But the mystery it requires your local ability. And how may the application looks like? It basically looks like from physics, life science, earth science, and some hand casting, meteorology or something, and computer science. And all of those are basically solving some super hard equation like PDE or FFT or something dense matrix multiplication or something like that. And they are super fun because normally all the results can be generated at a graph that are like now just given to us. For example, the weather that gives you the real-time weather forecast as a map. So how much the percentage of the raining from which location will be. And for physics, maybe they give you a simulation sequence of how they collision with each other or something. Yeah, so that's basically the application, but we all know that they are super hard math questions that requires the super cluster to solve. And also because the booming of AI, you also have something that is from AI, as Nell said, that we have a pre-trained model like GPT-3, like Yuan, which is a Chinese character version of GPT-3. They have some parallelization in terms of different methods, like data parallelization and model map parallelization in terms of deploying your models and how to train it. That requires your knowledge of how to distribute your data. And normally the PyTorch has a different backend. For example, NVIDIA's backend, like Nickel, which is another version of MPI. The MPI that has an MPI metrics for some reason, and also there has other like Alpha or Harvard backend for parameter to collide to merge. So we have all these applications like BERT, Transform, and microdollar macro. These are random AI that requires you to use all these metrics of parallel computing to make it converges faster. And also ISC has interviews. So as I said, you are studying in your desk, and some of the media will come to you, and you'll be famous like in a week or so, because it will directly publish on the YouTube. And also, judges will walk to the booth to talk to you after the competition, and it will in terms of a wide range of topics, like for example the diversity, how many girls, how many different cities are you from, like stuff like that. And SE interviews were more like academia rendering or something. The judges will have a detailed scoring test based on your result, based on your talks. And the poster part is as unique, so that the interviews will in terms of your poster. And also because last year, so SD19, it has a different metrics that it lets your mentor and your advisor to come to talk to your poster on the desk instead of you. So it will be a super fun of getting your advisor busy. It's rare. Okay, so for HPC friends, so from my perspective, so why? So when I was deciding whether to be a HPC guy or not, whether intending this, I thought like why those companies are not like recruiting PhDs in SC, supercluster domain. Rather, they will recruit like undergrad student. I think supercluster competition only gives you a basic hands-on experiment of how you're dealing with your clusters or something. But PhDs will definitely dig deeper into how one specific knowledge or specific experiment will how it carry out in a supercluster domain. For example, the parallel file system I proposed in previous slides are written by PhD students or proposed by PhD students, but the deployment of those things are done in a supercluster competition. So I think my answer is the companies want the people with the HPC application and deployment experiments so that they can, after you get into the company, you can co-work with those PhDs. So you can at least know that you can work for those PhDs for their required result. And for PhDs, if you want to dig it deeper, those SEC alumni, you can definitely go to a PhD industry. So definitely I go to the PhD journey. But those companies like NVIDIA and HRT, why they are recruiting those with the SEC alumni is because the hands-on experience really values, at least very valuable as for an undergraduate salary, right? So, so for the needs, like why NVIDIA or is recruiting is because they are producing the high performance chip. And for those who are super lucrative companies like HRT, which is a trading firm, they require like the high volume of data input and output for financial market. So they require a lot of HPC talents for like you to get into their company to maintain their data to make it at least competent in the market. So that's why they are recruiting SEC alumni. And every year we have different schools around the US and around the world go to SC, so you can get friends with them, and it's a great idea no matter you want to go to the academia or the industry. So the right bottom one is the PhD comment, which is super fun. Okay, so the general thoughts for optimizing HPC application is, so the fastest way is compiler option, so that when you are dealing with your MPICC or MPI-ICC, which is the Intel version of MPI-ICC, with different running time. For example, you can set the OMP threads or stack size for per threads. You can set these, and you can definitely gain some up gain for the performance for your application. And then we have a computer architecture fine tune, which is once you know after the profiling means you can see the graph of how much of different functions are taking how much of a time. And once you're going to the hot point of your code, you can see some of the computer architecture legacy code or computer architecture draining so much of time. You can fine-tune it using your computer architecture knowledge or different load balancing knowledge to optimizing the network, for example. That takes medium time but get a better performance than the a compiler option. Then you can transform your CPU to GPU or FPGA if the code are only given the CPU version of the code, because you know some of the code are easily being transformed into GPU code, and also you can use the latest compiler techniques. For example, OpenMP 5.0 gives you easy offload from your CPU code to GPU code. So you can give that an idea, and you can rewrite them in CUDA that makes your code automatically gain sort of like 50% or 5x time, performance. And the most time-consuming one is if you get the mathematic result and you see that the mathematic result can use another algorithm that can from ON to O1, that your result will definitely get better. But it normally takes a lot of time and requires a lot of people who are get into it. Like you have to co-work with other PhDs or something. And then for DevOps, normally we have the topology of 2 server because we don't have that much money and the power consumption limit. Normally we get our sponsored by NVIDIA or other companies. They are willing to get you paid for the server. And we connected with the InfiniBand, which is a higher, which is another primitive for TCP, but it does not have a checksum or other like 5 handshake or something. So although it's unsafe, but yeah, it has also some primitive like UDP and RD, but it's super fast. So it has something like kernel bypass stuff. That, so the Manilogs were bought, so that network driver were bought by NVIDIA already. So it's already NVIDIA. Normally every node we have 4 GPU because of the limit of the PCIe bandwidth limit. And we also connected through the Ethernet through this 2 server because we have to mount like NFS, like network file system or Lustre, and the Ethernet will not like occupy the extra bandwidth of InfiniBand. So it's sort of like a management port for Ethernet. And the right above one is the PMI and BMC, which will give you a basic I/O of how your chassis are working. So normally it gives you a chassis KVM so that you won't get to the into the loud, very loud server room to tune it. You can log in on a thing to get the basic I/O and basic management for the chassis. And Supermicro provides a BMC, and other like Dell, they has a different vendor things. And after installation, we have something called Grafana that you can monitoring your supercluster, like in terms of power, in terms of a CPU offload, CPU load, and the disk load, just like a time series database that give you a visualization for that. And our HPC composition, normally we have a dual Intel or AMD mid-range server processor for all computing purposes. So it's a general computing, so we have CPU, then we have a GPU, and as you can see, that's a version of a GPU. So what do you think through that? Like, what's the difference with your commercial 4090? Do you see the difference of that? this is only computation oriented, so it does not has a HDMI port. Is that interesting? Okay, so it's a V100 that's located in Shanghai Tech, which we wing them from the SC19. So it's pretty interesting once I first saw this. And also for storage devices, we have RAM DDR4 and do you know SAS? SAS is a different protocol by SATA, although they share the same lane, but they has a higher bandwidth and they has a control port for like disabling them or like maintaining heart rate or something. And the difference between the enterprise level SSD RAM with the commercial available ones, difference is normally the enterprise level has an ECC, which they has an error code correction for every checksum for the memory, because they want to maintain your memory system are not easily corrupted. Like, because for computation and storage, for normal storage, your data is sort of compared to the simulation or other scientific application are useless. So they think that the error correction are very useful for enterprise level. And also we have a non-volatile memory nowadays for external memory or SSD. This is between another hierarchy. And also we have to take other like FPGA and DPU for communication devices. And this is a data sheet for how A100 is listed. And we know that for int16 tensor core, its T-flops, sorry, maybe it's hard to see, but it's 1.3 T-flops for int16. But for int8, it has nearly triple their T-flops. It's because that the lower your bandwidth, the higher T-flops you gain. So sometimes if you're changing your precision of your application, you can automatically gain twice of the performance, although you may lose some of the precision of your computation. But sometimes the SEC will, the rules will let you not to modify the precision because of that. And also we can see the NVLink for the multi-node GPU connection rate. It's like 10 or 100 times than a PCIe link. So NVLink is super fast for, but your application should be aware of that schematic for how data packets are sending from one GPU to the other, not through the PCIe, only through the NVLink, and how those are getting faster using MPI cord bind or something. And this is our HPC DevOps. Normally we install the Debian, and in the end we have a NFS on ZFS, and we have a spec as a package management that you can automatically install through any compiler options through different compiler. And our compiler normally is GCC, ICC, and we also have AMD's AOCC. And libraries normally we have CUDA, BLAS, MPI, and FFT. So there's a lot of different FFT out there, but if we want to change them, normally we can gain 20% of the upgain for performance. And after profiling, we can know that where the least useful code is. We can remove some dead code and remove with some useful one. And also, as we shown on the prior BMC and Grafana page, that they give us a visualization and convenience for not going to the server room every time, so we can control them through Ethernet. And those are the system and the software management, and basically they are talked in the previous slides, but I want to mention that the AVX512 instruction set are useful for applications, but and also the heterogeneous computation are also newly talked like idea inside of HPC scenario. So once you can write some heterogeneous code, it will be better because some of the computation are faster in CPU and some of the computation are faster in GPU. So how do you communicate? Like once one is computed down, and some of the results are relying on each other. So you have to like give a standpoint of that whether it will be faster. Like prior, maybe you only use the MPI all to all. That will be a super drastically amount of time of getting communication done. So heterogeneous computing is also grading. So then we'll talk a little bit about the CPU and GPU fine-tune. So how to optimize the GEM software. GEM is basically HPL, two big matrix multiplication. So we need to know the miss penalty of different different hierarchy. For example, a register is less than 1 cycle and is less than 1 nanoseconds. And normally L3 takes 12 nanoseconds. And QPI, which is the NUMA socket, takes about 40 nanoseconds. And for DRAM is 65 nanoseconds. And this is a normal view. So the right above one is the original one. So that the for loop and do the M and K things. That's the gem. And we can first do something called loop enrolling, that we can better fulfill the I-cache and better fulfill the writing fetch for the internal loop because of the computer architecture. We know that the 8 int can fill in the cache line. So the loop enrolling is super useful for CPU design of the gem. So then we see that already gains a lot of performance for the little so the red line means a new one, but it's not that performant. And then we know that there's a vector extension on the CPU, which is called AVX2 or AVX512. So we can know that for a single instruction, we have the data parallelism for using multiple data and multiple ALU in a single vector, and we can make it in a single cycle or something. So we can just replace those loops with the vectorized instruction. So we can gain a lot of operating. So for the compiler nowadays, compiler is super smart. They can automatically optimize the loop for you. Replace those loops with SIMD if you tune the compiler option on. So you have to see the diffs of like -03 or CPU model equals to native, to see the changes of a compiled version of the application. And then we have MPI. So MPI, how much to hack inside. So basically MPI is a MIMD model. The previous vectorization is a SIMD, which is a Faxon toughness. So it's a term. So it means that the multi-machine can execute on multi-data in a same time. So there's something called UCX framework that can dynamically know the topology of your nodes are and do the right smart scheduling. So that's the MPI one. And the OpenMP, we have an OpenMP affinity that we can fine-tune a great topology that we know, because of this miss penalty for different socket will change a lot. But for OMP affinity, we can make this miss penalty less efficient to hide these communication errors, communication stuff. So, and for CUDA, we can rewrite those things into CUDA. but the compiler nowadays for OMP 5.0 is smart enough to automatically rewrite those applications to CUDA, but sometimes it's not efficient as for the code, but you can modify it after profiling. So CUDA is a SIMT model, which the T stands for the thread rather than the data. But it's super similar to SIMD, so you can do so with the model. And there's a lot of courses about CUDA over that. And I believe there's an application about 40% that's written in CUDA because the GPU are the main computing power in the nowadays supercluster. And that's the CUDA basics that use the thread ID and block dim.x and block index to get one SM to one block and to one single data storage inside the memory. So the CUDA kernel will launch this because it sends some code packets to the GPU, and GPU launch the kernel. So that's kind of consumer and producer model for CUDA. And as you can see, the difference between the vectorization, which is SIMD, with SIMT means the difference is their threads are running on a real string processor instead of one processor with different operand or different data placeholder. So and also with threads, the one string thread can with multiple thread blocks. That means this SM, and the grid means every grid can host that kind of the thread blocks. And the final thing is about core affinity, because we can aware of the AMD with a cache fabric that has a different CCX. So it has a bias of one CCX communicate with the other core's CCX. So we can, if we know that the 4 cores are communicated super frequently, we can assign only 4 core to those core ID. That communication will not necessarily to cross these core communication every time. That's how core affinity does. So we also have a Intel Xeon Broadwell, which is a V5 version 4. It's a RAIN bus in terms of the micro architecture. So every core are correlated in a RAIN bus, and there are if core from the above left to the bottom right, it has to go all the way through one half of the RAIN. And Intel, because the RAIN architecture we're designing now, for example, we get the Alder Lake and Raptor Lake for the 13 gen or 14 gen, we have only the RAIN bus. And the RAIN bus limitation is that we only have a 8-bit core on one RAIN. Although we can replace 2 or 4 cores with little cores that Intel replaced with Atom core, but the limitation is the core limit that compared with the AMD's CCX design. So Intel's for server, previously they add a RAIN buffer, add the RAIN architecture, and the RAIN bias, or they use the FIFO to communicate with the different cores. And starting from Skylake, they are using sort of like a mesh architecture, which there's a big pie and there's a mesh connected with each other, and they could put 28 cores on the die, but it still couldn't get close to AMD 64 core for 8 CCX. So for Intel's this kind of design, we know that the highest core is 28 core, and we can have SMT for 56 SMTs, which is a simultaneous multi-threading. But what if those low-end CPUs? So we all know that for after the CPU or outcome, they might have some bad cores out of the factory. So if the Intel architects knows that some of the cores are bad, they just disable it. So for the low end, they just outship the disabled core version of the full version of their mesh architecture. And for UPI and QPI, we said about the NUMA, they also have a bias, so we need the core affinity. And some misc is the CPU power, how to control it. We can set something in the bias. We can use a C state or P state, which is located in a Intel manual. You can set some random register to control the frequency that's running at the running time. And for certain, if you see the limit you want, just like threshold or down throttling. So that's how we control power. And the GPU power is simple. You just use the NVIDIA SMI or got it. And we can, sometimes a fan takes like 10 watts or 20 watts. So sometimes you can just disable your fans, although you get throttling. But that watts counts. So that's the hacking of the power. And also, how we optimize the operating system part, we can first do core isolation. Because if you want to do something like work scheduling, although the Linux claim that it has an O1 scheduler for red-black tree, but this is not what we want for certain workloads. So we can do like core isolation once the kernel is booting. We can know that there's no soft interrupts between the one core to the other. So we can physically find our cores on those cores, so we can prevent like C state change overhead and soft interrupt overhead. And also we have a kernel bypass. Like if we want to write to a NIC, we can use a user space network stack instead of a kernel space network stack. So once you put something in kernel, you will double copy your data. But using kernel bypass, you can maintain that your data will only maintain one copy of them throughout the processing in your OS. And also we have something like cache invalidation, page fault. These will be a penalty for the memory accesses. We have to disable them. And also, as we know that the kernel bypass outcome is zero copy and shared memory, to reduce the false sharing, something like in the cache or in the last level cache. And also we can avoid something like the thread lock. Normally in a pthread model, we have a spin lock, or we can change them into a lock-free data structure. That normally lock-free data structure, although they hold the last spinning time, but they can be faster when you are pulling from data from your data structure. So you can modify your code to realize this. And also we have a non-blocking, which means there's no context switching. So we can use a lighter context switching like a fiber or a coroutine to re-implement your code. It's also we have a process binding or something. And this is optimization work from Sunway Twilight, which is the prior top one supercluster on top 500, but now is surpassed by the LLNLs. I think it's brought by AMD. All AMD. It's Oak Ridge National Lab. So this is, but prior than that, their design are super different from the computer that we know. They're all many core design. So for many core design, we require the different core do not have any communication between each other, or less communication as possible, because the overhead of communicating between the cores are super high. So they re-implement the n-body simulation on that supercluster supercomputer, which gains a purely great result. But what their idea is using a hybrid process and hybrid thread, like to reduce their communications. The last one for that is the practice for undergrads is you can see those great GitHub repos and those courses from MIT CMU for the parallel computing and also some computer architecture courses by owner. Those will give you a general idea once you are optimizing those code. And also like other great talents blog. For example, I think the blog is the greatest food for thoughts if you want to dig something deeper. Other people has already gained the pitfalls because like someone in the Google has already implemented something. It should be like better than what you would have outcome. So like just see others' blog and reproduce others' results is a faster way of doing supercluster competition. And the other close combination, like I would definitely recommend VS Code because VS Code is good. So you have to know every hacks of how VS Code work. For example, it has machine to jump because normally most of the server are not connected to the network for the compute node, but for the storage node, they are normally connected to the server to the network. So you need to first jump into the logging node, then you use the SSH jump to another node, so that you can how you use it like auto login in your SSH and use VS Code to connect to that machine. And also we can use some AutoGen, make, CMake things for compilation. You have to get accustomed to those. And UEFI and ACPI things. And you can use JSON Nano or Raspberry Pi for those basic knowledge like grasp. And we require you to know something about the vTune profiler because the profiler can give you how your program will actually work on your machine. Because the general purpose CPU doesn't know any details of your application. And once you know that something that CPU get a hint, like a programming counter, give you a feedback, and you can use those feedback to optimize your codes too. So basically, the supercluster competition is you're making the existing code that's super tailoring to the CPU you're running to make it like unique to your general to your code, to make the general purpose more specifically purpose. That's what basically we're doing. And also we can sometimes we can just using the latency for your application to do the parameter tuning. Sometimes the simulation application can take 30 parameters, and every parameters may hurt or increase your performance for some reason. So you can use the reinforced learning auto tuning for tuning your parameters. And also you have to get a basic idea of how artificial intelligence, the latest pre-trained model working. And my final advice is learning by doing. So once you're getting to a competition, we'll teach you how to, we will at least advise you how to solve problem. And that problem, although the time you wasted on the like tool development and tool usage and the application fine tune will definitely give you a sight for how you do things in the future. And thanks. Yeah. Yeah. Can anybody call Nell to come back? I think I should go back to him. Yeah, it's all right. Yeah, maybe. I think it can be a Q&A part, and everybody can have chill. If you want to ask me questions, you can come up or in public. It's both are okay. Yeah, we have 40 minutes for that room.